My name is Ben Lehmann, and I came to MIT as a Pappalardo Fellow in 2022. And my goal as a fellow in the Center for Theoretical Physics is to understand the history and the constituents of the universe. There's a lot we don't know about the matter and energy in the universe, so sometimes the work takes us in unexpected directions. And I'm going to tell you about one of the directions I've been exploring that's really surprised me. This is work that came out of playing around with simple questions and following them down a lot of dead ends. So this is science that wouldn't have been possible without the freedom that I have had to explore, thanks to Neil and Jane Pappalardo. It's work that combines dark matter and black holes and close encounters in our own solar system. So let's start here in the cosmological context. This is a picture from a telescope showing a field of distant galaxies. But we now know that the galaxies that we see are just the tip of the iceberg of the matter and energy in the universe. If we could see the matter as it really is, it would look something like this. This is a picture from a simulation of dark matter in the universe. And what you can see here are dense clumps of dark matter in yellow. That's where galaxies form. And they're connected by these dark matter filaments that span throughout the universe, this big cosmic web. And in fact, most of the matter in the universe is dark matter. If we look at all forms of energy in the universe, here's how it breaks down. About 5% of it, this slice, is ordinary matter. That accounts for all atoms, all molecules, everything we can see. About 3/4 of it is dark energy. That's a different form of energy that's spread throughout the universe. It behaves pretty differently from matter. We know about it from the way that it affects the expansion of the universe. But the rest of it, about 1/4 of all the energy and about 80% of all the matter, is this invisible dark matter. And what's so interesting about dark matter is that it's not clear what this actually is. None of the particles that we know of can account for all of the dark matter, so this has to be something new. Dark matter is one of the strongest hints we have for new fundamental physics beyond those particles that we already know about. And in many ways, it's a key to understanding the universe at its earliest moments, too. So it's frustrating that we seem to know so little about it. But I actually want to give you a different perspective. I would argue that we actually know a lot about dark matter. Let me give you a quick summary of some things we know. We know, for example, that dark matter is cold. That's a technical term. Really what it means is that dark matter particles are slow moving. The hotter a gas is, the faster the particles in it are moving around. We know that dark matter gas is cold. We know that dark matter is dark, or really invisible would be a better word. Specifically, we have very tight constraints on how much it can reflect or emit light, and even on how much dark matter particles can scatter or interact with each other. We know that dark matter is matter. Its energy density does not behave like radiation or like dark energy, and we know precisely how much there is, about to the percent level. We know that dark matter is clustered. Dark matter can collapse into structures across a huge range of scales. We actually see that structure in the universe. It's imprinted in the arrangement of galaxies on the sky. It's a beautiful match between theory and experiment. We know that dark matter is stable. It decays very rarely, if at all, into other particles. And finally, we know that dark matter is galactic. And what I mean by that is that galaxies are actually born inside clumps of dark matter. So the physics of a galaxy is very tightly connected to its dark matter environment. We're in a galaxy right now, so that means we're actually inside a dense clump of dark matter. And not only that, but galaxies actually wouldn't form without the presence of those dark matter clumps to begin with. So in a way, dark matter is one of the reasons that we're here at all. So for these reasons, I sometimes get kind of annoyed when people say that we need to discover dark matter. I would actually say that we have already discovered dark matter. We see it in many different contexts, playing lots of different roles in the universe. The goal is not to discover dark matter. The goal is now to be able to understand the physics of dark matter. So with that in mind, let me show you what we're up against. This is, roughly speaking, a plot of the parameter space where dark matter might live. The horizontal axis is the mass of a dark matter particle, and the vertical axis is the strength of its interactions. Now, we know that dark matter interacts at least through gravity, so that sets the bottom of the vertical axis. And we also know from galaxy physics that the mass has to be at least 10 to the minus 20 eV. That's very small, but it's not zero. And we know from lots of other observational tests that there's also a maximum mass for dark matter particles. It's a little bigger than the mass of our sun. So that's a big range. The break in the axis, that's hiding 40 ticks. That's 40 orders of magnitude there. So there's a huge range of parameter space to explore here. And for many reasons, as a community, we've spent a lot of our effort over the last few decades focusing on one spot in this parameter space. And that's what we call the weak scale. So the weak scale is a mass scale. It's about the mass of the Higgs boson. And it corresponds also to an interaction strength like that of the weak nuclear force. And there's very good reason to think that new particles might exist in this region. And a very successful generation of experiments was built largely to test that idea. But so far, we have not found anything. That does not mean that we stopped looking under this spotlight. This is still a very important piece of the parameter space. But there's also broad agreement in the community that it's time for us to be more open-minded and to consider possibilities all over the parameter space. And this is extremely challenging. There's all kinds of really different physics at different points in this plane, and there's no one experiment that can test everything. This is really the problem in dark matter science right now. So how do we solve the dark matter problem? Well, I want to give you my perspective on this. The philosophy of dark matter science used to be that we would quickly identify the microphysics of the particle or particles that make up the dark matter, and then we would use that particle physics to tell us about the properties of dark matter. So it would tell us, for example, whether the dark matter is composite, made up of other particles, whether it's multiphase, and it goes through different phases over the history of the universe, if it is interacting with us or with itself, if it's multi-field, if it's made of many different kinds of particles, if it's dissipative, if it makes structures like stars, if it's thermal, so if it's produced out of the hot thermal soup of the early universe, if it's wave-like, if there are long-range quantum effects, or if it's granular at the other extreme, if it's concentrated into little clumps or objects. Well, we still don't know the microphysics of dark matter. But what we can do is turn this picture around. We can use these large-scale behaviors. We can go after them. We can actually look for them, observe them directly, and use them as a way to understand the particle physics of dark matter. So that's the core of how I approach dark matter. My program is based entirely on using new tools that weren't necessarily developed for dark matter physics at all to look for these broad, large-scale properties of dark matter. And just to give you a taste, there are a lot of new tools that we have now, or that we're going to have soon, that are really promising for identifying these large-scale behaviors. There are tools like quantum sensors, precision cosmological observables, gravitational waves. For this talk, though, I just want to focus on one tool and just one of these broad features. And that's granularity. So what do I mean by granularity? Here, I want to return to the parameter space of the dark matter particles' mass and interactions. I keep saying that dark matter is a particle, but that's really only the right description in part of this plane at intermediate masses. So here the particles behave like a gas. There's lots of them. They each move around independently. But there are two other possibilities. So first, remember that in quantum mechanics, particles also have wave-like properties. And as the mass goes down, the quantum mechanical size of the particle, the wavelength, increases. And at some point, once the mass is low enough, these waves start overlapping and interfering with each other. And the behavior of the dark matter becomes very different in some important ways. It can't be treated as a gas of particles anymore. On the other hand, if each particle or each dark matter object has a very large mass, well, there must be fewer of them. We know the total amount of dark matter, that's fixed. So in that limit, the dark matter doesn't necessarily look like a gas so much as a collection of heavy chunks of material. And that's what I mean by granular dark matter. Now, one of the things that's so interesting about granular dark matter is that there's an obvious physical candidate, and that's black holes. Black holes are incredible objects. They fit all the requirements for dark matter. And we've gained a lot of new tools for studying them in just the last 10 years or so. So for example, this is a picture of a black hole taken by the Event Horizon Telescope, achieved just a few years ago. But I do want to be clear. This is a picture of a massive black hole at the center of a galaxy. And when I talk about black holes as a dark matter candidate, this is not what I'm talking about. We know that dark matter is spread out all over the universe, and it's present throughout the history of the universe. So if dark matter is made of black holes, then those black holes can't be made by stellar death in the late universe. They have to be produced all over in the early universe. And there's actually a pretty easy and natural way to do this. If we go back to this simulation of dark matter, you can see the matter in the universe is not spread out evenly. There are fluctuations in the density from place to place. And those fluctuations, those seeds of structure in the universe, originate from the very early universe. If those fluctuations were big enough in some places in the universe that those regions never expanded, but just collapsed on themselves, that would give us black holes directly from the plasma of the early universe. Those are the black holes that could be dark matter, and so we call them primordial black holes. Now, primordial black holes have been studied for a long time as a candidate for dark matter, so there have been lots of observational tests across lots of black hole masses, and this plot is showing a set of constraints from different experiments. The horizontal axis here is the mass of the black holes, and the vertical axis shows the fraction of dark matter allowed in black holes of that mass. So if we want to explain the dark matter with black holes, we have to be able to reach the top of this plot, 100%. Now, there are some particularly interesting areas here. The first of all, at very low masses, this orange constraint actually faces some important uncertainties. So it's possible that dark matter can be made of black holes all the way down to the Planck scale, very far below the bottom of the plot. There's another interesting island around the mass of the sun. A lot of models end up producing a small fraction of dark matter there because of the properties of QCD, strong force. And I've been working on several projects that are actually probing both of these possibilities using gravitational waves, where we have a huge amount of new data and there's so much more to come. But if we want to account for all of dark matter with black holes, there is an obvious place to put it, and that's here. This gap in the constraints between about 10 to the 17 grams and 10 to the 22 grams, that's what we call the asteroid mass range, because these are kind of like masses of heavy asteroids. Looking for these objects is extremely challenging, and it's easy to understand why that is. These black holes have the masses of asteroids, but the sizes of atoms. These are microscopic. And not only are they microscopic, but they're very rare. So remember, black holes as dark matter are granular. The total amount of dark matter mass has to be spread out amongst heavier objects, so there are fewer of them. And that means instead of like a gas of particles where any box contains just about as many particles as the next, these black holes are scattered all around the universe. There are large distances between them. In the asteroid mass range, the typical distance from one black hole to the next is about 1 billion kilometers. So to give you a sense of scale, that's roughly the size of the solar system. That makes it extremely challenging to detect a black hole like this. Ordinarily, a dark matter experiment watches for particles passing through a detector on Earth, like this one. But given the spacing between dark matter as black holes, we would literally need a detector the size of the solar system. Now, what I'm going to explain in the rest of the talk is that we actually do have a detector the size of the solar system, and it's the solar system itself. I'm talking specifically about ephemerides. I know this sounds like a Greek hero. It's actually just the term for records of the positions of objects in the solar system over time. And this, as you can see, is something that people have been doing for a very long time. Of course, we've gotten better at it over the last 100 years or so, and now we have a lot of precision data on the movements of planets and other objects. So let's ask the following question. If dark matter is made of black holes, and one of these black holes passed through the solar system, could that leave an imprint in the historical record? Could we detect a black hole just by measuring distances precisely? Now, to answer this, we first need to know how precisely we can make those measurements. Instrumentation has improved a little bit since the ancient Greeks, and with apologies to Obi-Wan, this actually is the moon. This is a picture of lunar laser ranging, where we bounce lasers off of mirrors left on the moon by astronauts. This gives extremely precise measurements of the distance from the Earth to the moon. We can actually do almost as well with Mars because we have orbiters around Mars and rovers on the surface. So, and this is a shocking number, we actually have been able to measure the distance to Mars to within about 10 centimeters for the last 20 years. It's just incredible. That was a huge surprise to me. But this is the result of a lot of clever engineering. And now we can use that to do some clever physics. So now, knowing how precisely we can estimate distances, let's ask by how much a black hole could perturb those same distances. And I want to start with an estimate you could do with pencil and paper. Let's imagine that a black hole passes by Mars. It starts off at some point along the x-axis. It has some velocity v0. It has some impact parameter b, and it's moving quickly compared to Mars. We know that about dark matter. So given this information, we can approximate the impulse velocity, delta v, that's given to Mars just by the gravity of the passing black hole. Looks like this. That velocity given to Mars is going to make it drift with respect to Earth. So the distance that we measure is going to change slightly over time. Let's say we watch for a time delta t. So roughly, if the drift is larger than the measurement precision, that's sigma r, this is something we could see. Now, if you fix the observing time, you can turn this around to say that black holes are observable if they pass within some maximum impact parameter, a distance, Bmax. And now I can combine that with the properties of the dark matter distribution to get the rate of observable events. Here's what that looks like. So I computed this assuming a black hole mass of 10 to the 20 grams, right in the middle of the unconstrained range, and I've assumed a 10 centimeter measurement precision. With those numbers, we should be able to see about one event every 26 years. And that's an exciting number because we already have about 20 years of data. And this is a very simple estimate. So with a more sophisticated calculation, we might turn out to be sensitive to lots more than just one every 20 years. Now, the step after this pencil and paper calculation was a simple simulation. So I worked on this together with an incredible undergrad, Tung Tran, who put together a simple model of the solar system on his laptop, and he threw in a primordial black hole. You can see it in this picture coming down through the plane of the solar system. And from simulations like this, Tung calculated the change in the distance that we would measure to different planets. That's what this plot is showing as a function of time. There are 3 different planets here, Mercury, Venus, and Mars, and you can see there's a complicated time dependence. It's definitely not as simple as the pencil and paper calculation, but that pencil and paper result is actually represented here by the dashed lines. And you can see that while they're not in perfect agreement, they are similar at the order of magnitude level. So the simulation model also suggests that this observation is possible. Now, I combined this simulation model with the dark matter distribution, and I came up with the first estimate of the actual rate of observable events. That's what this plot is showing. The horizontal axis here is the black hole mass, and the vertical axis is the number of expected detections per year. There are 3 different colors here, and that corresponds to different estimates for how well one can really extract small signals from noisy data. The idea is to look for a particular waveform, a particular time dependence in the signal, in that distance that we measure to a planet. And there are statistical techniques based on matched templates for detecting signals like this. So here I parameterize the sensitivity of those methods by this number Q0. Now, ultimately, Q0 depends on the quality of real data and on the quality of full-scale simulations. So it's hard to say exactly what this number is, but the blue curve, the most optimistic one that I'm showing, that was chosen to be similar to the efficiency of similar techniques used in the LIGO experiment for gravitational waves. And now, since we have about 20 years of data, we really want to get above this horizontal bar. That's where we can detect black holes with the data we have. And you can see that under the most pessimistic assumptions, the green curve, we should be able to detect black holes around 10 to the 17 grams. That's at the low end of the asteroid mass range. On the other hand, if we do as well as LIGO, then the blue curve applies. And here we can essentially test the entire unconstrained region. And finally here, I want to point out that this plot, this is made assuming that we only use one object, only the distance to Mars. In reality, we have other planets that we can measure at the same time, and we can use correlations between them to do even better. So what this result tells us is that it is possible to detect black holes this way, but to actually do it, we need full-scale simulations. The input for this plot was made with a simple toy model of the solar system, about 20 objects, something that could run on a laptop. To model the solar system with enough precision to generate real tests that can be applied to real data, we've got to go a lot further. Now, fortunately, we are not the only people interested in modeling the solar system. Precision simulations of the solar system are a well-established business, and there are 2 groups with particular expertise here. First, JPL maintains a model called DE441, and second, the Paris Observatory maintains a model called INPOP21A. These are very sophisticated models. They include more than 2 million objects in the solar system. They include a huge range of physics that isn't incorporated in the toy model on my laptop. They incorporate tidal dissipation, radiation pressure, relativistic corrections. So needless to say, these are extremely complex simulations that take some serious computing power. And it is well beyond my ability to just take one of these models and throw in a black hole. But I know some people who can do just that, and it's the Paris Observatory group. We've been in contact with them and talking about what steps we need to take to bring on the next stage of this concept and actually perform high-fidelity simulations to generate realistic data that can be directly compared with observations. So the near future is very exciting. But as it turns out, even the present has been quite exciting. Together with Tung Tran and with Dave Kaiser and former student Sarah Geller, we published these results about a year ago, and I want to highlight some of the responses from the rest of the community since that time. So quite soon after we put out our work, another group suggested that maybe you could do the same thing with GPS satellites, since we can measure their accelerations very precisely. And that actually might work particularly well for even smaller black holes. From the observational community, there has been work on detectors that might be used to study asteroids that could be a background for this kind of search or to follow up on a candidate signal. There have been other claims in the community about the possibility that solar system data might already rule out black holes as dark matter. And that has spawned some further conversation and further numerical study that's given rise to a clearer picture of what's needed to realize these constraints. This is just a sampling. There have been many other papers building on our work. But equally fun has been the response from the popular press, because as it turns out, people get really excited about the idea of black holes as dark matter, and they get even more excited about the idea of black holes passing through the solar system. So APS's Physics magazine published an accessible summary of our work, and that was followed by a piece from Science News, and another one from Scientific American, and then one from the LA Times. But I think my favorite is this video explanation from the PBS Spacetime series. And I know this was getting to a fairly wide audience because I actually didn't hear about it from them. I heard about it from my dad, who encountered it in the wild and thought I might be interested. And, well, I was interested. Now, finally, I want to wrap this up by returning to the context of black holes as dark matter. Remember that apart from a couple of islands that I'm working very actively to test, dark matter can only be made of primordial black holes if they fall into this asteroid mass range. So far, no experiment has been able to test black holes as a dark matter candidate in this window, but in the coming years, as we work together with experts in solar system modeling, as well as a whole host of other probes, I expect us to be able to test this entire window. And what that means is that we are coming close to a decisive test, not just of asteroid mass black holes as dark matter, but really the entire idea that black holes might be a dark matter candidate. And even more generally, that dark matter is granular at all. We should soon be able to say whether dark matter behaves more like a gas or more like a collection of dense objects. And that brings me back to the broader strategy. The whole story I've told you is geared at answering one question of a set of questions, one plank of a broader collection of ideas that each tell us something about the physics of dark matter. The future of dark matter physics is all about leveraging all of the tools at our disposal to cover all these bases and to understand the new physics wherever we can see it. So whether or not we figure out exactly what the dark matter is, there is a lot that we stand to learn about dark matter imminently. There are many concrete questions we can ask and many new tools available to answer them, even tools right here in the solar system. I want to end this talk by acknowledging many wonderful collaborators, especially Tung Tran, Sarah Geller, and David Kaiser, who are my collaborators on the work I just told you about, but also to many people, many places here at MIT, across lots of institutions who are helping me push these ideas forward. And so much of all my work, but really this work in particular, is really owed to Neil and Jane Pappalardo. They've put together an incredible group of people in an incredible place. They've given us the opportunity to chase after crazy ideas and made us almost like part of the family at the same time. So thanks again to all my collaborators, and thanks again to Neil and Jane.